When students take real analysis, they're usually already familiar with the concept of continuity. But then they're introduced to different flavors of continuity, such as uniform continuity, absolute continuity, and Lipschitz continuity. Now at first, as a student, I was annoyed at having to learn all these variations. But much later on, I realized just how powerful they were, how much easier they made it to prove certain big theorems, and how lucky I was not to be named Lipschitz. In this video, we will give a lightning-fast review of regular old continuity. We'll introduce the totally awesome concept of uniform continuity, we'll prove a big theorem about uniform continuity, and finally, we will show a super straightforward and super awesome application to integration theory. Let's get started. In real analysis, you learn about regular old continuity. Just to remind you, we say f is continuous at some point c if for every epsilon greater than 0, there's some delta greater than 0, so that whenever your x value is within delta of your point c, the y value will be within epsilon of f of c. I think the best way to understand continuity is to look at the ways a function can fail to be continuous at a point. The simplest discontinuity is a removable discontinuity, and that means that the function has a limit at that point, but the limit just doesn't match the function value. Another discontinuity occurs when the left-hand limit and right-hand limit both exist, but they don't equal each other. That's called a jump discontinuity. And you can have an essential discontinuity. That means that the limit doesn't even exist at that x value. Now there's another type of continuity called uniform continuity. This is going to be a stronger condition. In other words, every uniformly continuous function is also continuous. Now for regular old continuity, we're given an epsilon and an x value, and we have to find a delta for that point and that epsilon. But at a different point, we might need a different delta, for instance, if the function is steeper there. But for uniform continuity, we need one delta that works for every point simultaneously. So let's look at the definition of uniform continuity. For every epsilon greater than 0, there must be a delta greater than 0, such that for any two x values, x1 and x2, if they are closer than delta units apart from each other, then their y values are less than epsilon away from each other. Notice that delta depends only on epsilon, not on the specific point. To give a quick example where this fails, just consider 1 over x on the positive reals. If I pick two really tiny x values, their y values could differ by an arbitrarily large amount. So you can't specify delta until you know just how small x is going to be. To make this rigorous, let's say you claim that this function was uniformly continuous. Now I can pick an epsilon, let's say epsilon equals 1, and no matter what value you pick for delta, I can pick an integer n bigger than 1 over delta. Let's let x1 be 1 over n, and x2 be 1 over n plus 2. They are within 1 over n of each other, so they're within delta of each other, but their y values differ by 2, which is bigger than epsilon. So no matter how tiny a delta you pick, I can pick those two x values so that the y values are more than 1 unit apart. An even simpler example is the function y equals x squared on the whole real line. If I pick epsilon equal to 1, then no matter what delta you pick, I can pick an x bigger than 1 over delta. Then if our x values are x and x plus delta over 2, the difference in y values is, after some algebra, bigger than x times delta, which is equal to 1. So no matter how small you pick delta, I can find points within delta of each other where the function values differ by more than 1. Now let's look at the function y equals mx plus b on the real line. If someone picks an epsilon greater than 0, I can just let delta equal epsilon divided by the absolute value of m. And I should point out that in the case where m is 0, you have a constant function and you can pick any number for delta. When m is non-zero and the distance from x1 to x2 is less than delta, then we can do some algebra and find that the absolute value of the difference in their function outputs must be less than epsilon. So this function is in fact uniformly continuous. Now in that example, we had a constant derivative, but we can take it a step further. Let's say that we know that our function is differentiable and the derivative is bounded. Then we can still say that the function is uniformly continuous. So suppose f prime is always less than big M in magnitude. Again, we can pick any positive epsilon and let delta be epsilon over big M, so m times delta equals epsilon. Now, pick two x values less than delta apart, and suppose that the difference in their function values is greater than epsilon, which equals m times delta. But we know from the mean value theorem that the difference in function values must be the difference in x values times the derivative for some intermediate point. But that first term is bound by delta, and the second term is bound by big M, so the left-hand side is actually less than big M times delta, which is a contradiction. Before we get to our big result, we need a quick refresher on compactness. A set is said to be compact if every open cover of the set has a finite subcover. So if you have a collection of open sets whose union is a superset of your set K, then there must be some finite subset of that collection that also covers K. And the Heine-Borel theorem tells us that in Rn, being compact is equivalent to being closed and bounded. Now the big result is that a continuous function on a closed bounded interval is necessarily uniformly continuous. Now you can skip this proof if you want, but I'd encourage you to follow along. It ties together some really important ideas from real analysis. So just to preview the excitement, first we will apply the definition of regular old continuity, not just once, not twice, but uncountably many times. Then we will use compactness in a subtle but critically important way. And oh yeah, we'll then use the triangle inequality about 50 or 100 times. So here's the proof. To quickly outline the argument, once we have an epsilon, the definition of continuity gives us a delta interval around each x. By compactness, we can cover the entire interval with just finitely many of these delta intervals. Then we pick the smallest one, and that should give us a delta that works for every x value. Well, sort of. There are some important details which we will now flesh out. So let's get into all the details of the proof. F is a continuous function from the closed bounded interval from a to b, and we want to show that f is uniformly continuous. So we let epsilon be greater than 0, and our goal is to generate a delta such that any two x values that are less than delta apart have y values that are less than epsilon apart. Let's start by using continuity at a single point x. Now if epsilon is greater than 0, then epsilon over 2 is certainly greater than 0, and the definition of continuity says that we can pick an interval around x, let's say it goes delta sub x in each direction, so that for every t in that interval, we can guarantee that the absolute value of f of t minus f of x is less than epsilon over 2. Why did we pick epsilon over 2? Well, let's say we pick 2 points in our interval, call them s and t. Since each of their y values are within epsilon over 2 of f of x, that means that their y values must be within epsilon of each other. So that's an important fact to remember. Now let's shrink that interval so that instead of having a radius of delta sub x, it only has a radius of delta sub x over 2. Now watch what happens. Let's pick an s within delta sub x over 2 of x, so that's inside this new smaller interval, and then pick a number t within delta sub x over 2 of s. Both s and t are within that original delta sub x interval, so their function values must be within epsilon of each other. So to summarize, if we cut our interval in half, then we can pick one point in the interval, then pick another point, delta sub x over 2, away from that point, then those two function values will be within epsilon of each other. Now notice that I'm using delta sub x instead of just regular old delta. That's because I want to emphasize that for the same epsilon, the delta we pick could depend on x. But let's go ahead and pick a delta sub x for each x in a to b and form these half delta intervals. Now this clearly gives us an open covering of the interval a to b. After all, we have an open set for each point in a to b. But here's where compactness comes in. Since the closed interval from a to b is compact, there must be a finite collection of those open sets that cover a to b. Since there are only finitely many of those open intervals, we can just take the smallest one. Let's say this was the interval around x star with radius delta sub x star over 2. We've been looking for a single delta that works for the entire interval, and I claim that this is it. So we will let delta be delta sub x star over 2. Now let's show this delta works as advertised. Let's pick s and t in the interval from a to b so that they are less than delta apart. We know that s must be in one of those open intervals covering the entire interval a to b, and that interval must have radius at least delta. That's the way we chose delta after all. Now t is at most delta away from s, so it could be outside this thicker purple interval, but it can't be outside the original full-size interval of radius delta sub x. Finally, since s and t are in the same original delta sub x interval, their y values are less than epsilon apart, and we're done. Just to recap this totally amazing argument, pick an epsilon greater than 0. For each x in our interval a to b, pick a delta sub x such that for all t in the interval x minus delta sub x to x plus delta sub x, f of t is within epsilon over 2 of f of x. Now for each x in our interval a to b, form an open interval of radius delta sub x over 2. This forms an open cover of our domain. Since it's compact, we can find a finite subcover, and since it's finite, we can take the minimum radius of all those open intervals and call that radius plain old delta. Finally, take 2 points in a to b, call them s and t, that are less than delta units apart. S must be in one of those delta sub x over 2 intervals, so s and t are both in the same original size delta sub x intervals. Both s and t are within delta of x star, so their function values are both within epsilon over 2 of f of x star, and therefore their function values are within epsilon of each other, QED. Now let's see an important application of this result. One of the ways to introduce integration in real analysis is to look at something called the Darboux integral. If you take a bounded function on some interval a to b, and you take a partition of that interval, meaning you just pick a sequence of increasing x values that starts at a and ends in b, then you can define the upper Darboux sum for that partition by taking the width of each subinterval times the supremum of the function on that subinterval, and then summing them up. Similarly, you can take the lower Darboux sum by taking the width of each subinterval times the infimum of the function in that subinterval, and adding them all up. The idea is that as the width of the subinterval shrinks, these upper and lower sums should close in on some limit. And without getting too deep into the weeds, you can show that a function is Darboux integrable if and only if, for every epsilon greater than 0, there's a partition where the upper and lower sums are less than epsilon apart. Just to show a quick example of a function that is not Darboux integrable, take the function that is 1 at every rational x value and 0 at every irrational x value. No matter how tiny we make those subintervals, every one of them will contain a rational number and an irrational number, so the upper sum will work out to be b minus a, and the lower sum will be 0. But if we take a continuous function on a closed bounded interval, we can always find a partition that makes the upper and lower sums as close as we want. This is far from obvious, but if you use our previous result about uniform continuity, the proof almost writes itself. Of course, it doesn't actually write itself, but you might want to pause and try to write it yourself. Or you can wait another 3 seconds and we'll write it for you. Okay, here goes. First, let epsilon be greater than 0. We need to generate a single partition of the interval so the upper Darboux sum minus the lower Darboux sum is less than epsilon. Our previous theorem says that f must be uniformly continuous, so we can pick a delta greater than 0 so that for any two x values in our interval, call them s and t, that are less than delta apart, their y values must be within any small number that we specify. In this case, we'll require them to be within epsilon over b minus a. Why that number? It'll become clear very quickly. Just take any partition of the interval where the longest subinterval is smaller than delta. Now, when we compute the upper sum minus the lower sum, we can just write this as a single sum where each term is the width of the subinterval times the difference between the sup and the inf of the function in that particular subinterval. Now, I should note, on each of these subintervals, we're dealing with a continuous function on a closed bounded interval, so the function will actually achieve those values, the sup and the inf. This is known as the extreme value theorem, and it's typically covered long before integration. But in case you want a refresher, we proved this result in our real induction video. Anyway, the point is that when we take the difference between the sup and the inf of the function on each subinterval, we're subtracting two actual function values in that subinterval, and since the x values are less than delta apart, we know that the function values must be less than epsilon over b minus a apart from each other. So simplifying a bit, the right-hand side just turns into epsilon over b minus a, all times the sum of the lengths of the subintervals, which of course is just b minus a. So the right-hand side is just epsilon, and we're done. This is an amazing result about integrability that followed easily from uniform continuity. I hope we've convinced you of the overall awesomeness of uniform continuity. We always appreciate your feedback in the comments, and if you give us a thumbs up, that will help the algorithm show our video to more math-obsessed viewers out there. Thanks for watching.